Hello, everyone. I'm Vedhi, and I'll be the MC for this session. It is my pleasure to introduce the speaker for this session, Kevin Esvelt. Kevin is an MIT professor who leads the Sculpting Evolution Group in exploring evolutionary and ecological engineering. The creator of a synthetic ecosystem to rapidly evolve molecular tools, he helped pioneer the development of CRISPR genome editing, but is best known for his invention of the CRISPR-based gene drive systems capable of single-handedly editing wild species. He has led efforts to ensure that all research in the field is open and community guided, while calling for caution regarding potential misuses of biotechnology. Esvelt's laboratory broadly focuses on the developing new molecular tools, mitigating catastrophic biorisks, improving animal welfare, and improving scientific norms to favor early stage review. Today, Kevin will be talking about mitigating catastrophic biorisks. We'll be starting with a 15-minute talk by Kevin and then move on to a live Q&A where he will respond to some of your questions. You can submit questions using the box to the right-hand side of the video, and you can also vote your favorite questions to push them higher up the list. So here's Kevin.
Thank you for the kind introduction, Vedhi. So security experts have a saying that I just ran into a couple of weeks ago and I absolutely fell in love with. So I thought I should really open this talk with it. And they say any system that is vulnerable to accidents is helpless against a deliberate attack. The state of the world right now makes that statement rather more troubling than usual because COVID-19 is an accident. It is not a deliberately designed virus. And it's not even a particularly devastating accident compared to historical pandemics, many of which killed a very large fraction of the relevant population. The most recent one, of course, 1918 influenza, is thought to have killed as many as 50 million people, although that was only 3% of humanity at the time. Even more concerning, all of these accidental pandemics were, of course, created by evolution, which is not trying to kill people. If you take 1918 influenza, a mutant variant of that virus that is more effective at killing people is not going to be favored by natural selection because a dead host does not spread the virus very effectively. In fact, usually it's the opposite. Pandemics are devastating because they jump into our species and they're poorly adapted to us. A deliberate attack would be much, or at least would have the potential to be much more devastating than any of these historical pandemics. This suggests that given that we have struggled to handle COVID-19, that we cannot withstand a deliberate attack made by any kind of sophisticated attacker. So it's very fortunate that today we probably don't know enough to mount such a deliberate attack. And ideally, no one will learn how to attack until we can adequately defend. This gets to the broader challenge of biotech. Biotechnology is hazardous because viruses like SARS-CoV-2 are exponentially spreading, and it's possible that through biotech, they may become accessible to very large numbers of people. I always analogize pandemics to wildfires because they similarly can spread exponentially. And the risk that we face is a world in which tens of thousands of individuals have access to the biological equivalent of matches. That is what we must prevent. Now, we know that exponential spread is possible by design. And in fact, CRISPR-based gene drive is, as far as we know, the only example right now that we believe could be engineered to spread on its own in the wild without human intervention. There are many other plausible ways of doing it, but this is the only reliable one that we believe we know about. The problem is, it isn't particularly well known, and even if it were sufficient justification that we should be concerned about the possibility of engineered viruses that could do the same thing, that would have positive fitness in the environment once released. The problem is that most scientists who are seeking to mitigate pandemics are really not aware of security issues, or at least only in the loosest sense. And that means that their model of what they're trying to prevent is focused on natural pandemics, which normally goes, okay, there's a zoonotic virus out there somewhere in the wild. It may evolve to hit a new sequence that would allow it, in the event that it were exposed to humans, to jump species, enter our cells, replicate, and begin spreading from person to person efficiently enough to cause a pandemic. So in order to prevent this, they first want to know what we're facing. So many scientists today plan to sequence as many zoonotic viruses as possible from other mammals and birds, study all examples of a virus jumping species to learn mechanistically what is it exactly that makes a virus pandemic? What are the determinants of viral fitness in the wild? And then using that information, they want to create predictive models of pandemic risk for particular zoonotic viruses of concern. That would let us identify which ones are most likely to jump, and therefore the ones that we need to potentially do something about. And once we have our list of highest risk candidates, we could then develop vaccines in advance or intervene by, and here people tend to mumble because we don't really have any idea how to intervene, but still, surely knowing about it would be helpful, right? Well, there's a problem. Let's just assume that we have this toy model of biological wildfires. Prevention, in order to prevent a naturally occurring biological wildfire from starting, we would need to take that predictive accuracy. Does this thing have the potential to spread in the wild, this particular sequence variant of something that's out there? What are the odds of it evolving in the wild? This is a hard problem. We're not good at predicting how viruses will evolve even in the laboratory. What are the odds that it will actually jump into humans? And what are the odds that we will be able to do something about it? All of those things need to happen for us to successfully prevent one that would otherwise have caused a pandemic. In contrast, once we have that predictive model of what is required for a virus to take off, then as long as it's not terrible, then anyone with skill and access to relevant viruses could plausibly make it, which means it's down to the number of people in that category and the individual odds that someone will actually do it for whatever reason, ideological, mental illness, what have you. So to get more concrete, if we suppose that the predictive model is 10% accurate, that is, the highest risk viruses that they spit out actually have a 10% chance of taking off in humans. Well, even if we assume that we're perfect at every other factor in the prevention equation, we perfectly know whether it will evolve and jump species into humans, and we have an intervention that is guaranteed to block it, then we'll still need to develop and apply such interventions for 10 viruses in order to prevent one natural pandemic. In contrast, something with 10% accuracy would theoretically allow anyone with the relevant skills and access to build 10 candidates in order to deliberately start a pandemic. And of course, they might also be able to engineer it in such a way that it would be worse than a naturally occurring one. And given what we have seen over the past year, this overall suggests that pandemic biology appears to favor offense. And what that means is that if this is correct, which it may not be, the expected value of acquiring and disseminating information on viral fitness appears to be quite negative. So whatever we can do to dissuade researchers from going down that path seems to be highly worthwhile. That's not to say we can't do anything at all to defend against pandemics. Of course, there are many things that we can do to build up our defenses, and we should build these because the risk of a zoonosis jumping into humans is about 1% per year if we restrict it to the category of SARS-CoV-2-like or worse. And at $16 trillion to the US economy alone, let alone the rest of the world, it's definitely worth investment in prevention. So the number one thing we can do is, in fact, early warning, but not figuring out which viruses are at risk. Rather, we should rely on sequencing because everything is made of nucleic acids. So environmental metagenomic sequencing, just sequencing everything in an environmental sample, will allow us to establish a baseline of nucleic acid diversity in a given location. Then, if we continually monitor by sequencing samples from that location, we can detect any exponential agents that are spreading because that will be a deviation from the baseline. It doesn't matter what they are. We don't have to know anything about them. We just have to know that they're appearing and becoming much more common very quickly. And that is the signature of an exponentially spreading and therefore threatening agent. We can also monitor building wastewater, treatment plants, waterways, travelers, patients. These are the places where we should be sequencing from. We also can begin preparing in advance. Now, this is difficult because we don't actually know what the agent might be. But we do know that if we're concerned about pandemics, it spreads from person to person. And so we need to maintain and even improve our current contact tracing systems, ideally making them bidirectional and supporting with digital measures like the exposure notification systems. And we can also begin preparing defenses on the molecular scale. We can't build vaccines without knowing what the virus is, but we can build a decoy version of the receptors used for all known receptors used by mammalian viruses. There's only several dozen of them. If we can build a decoy that is soluble and can bind to any virus that uses that receptor, and we have one and get it approved for every known receptor, then we would have those interventions ready to go. We should also work on solving the cold chain problem, because unless we do that, no matter what our defenses might be, we will not be able to protect the bottom 3 billion people from the consequences of either accidents or deliberate misuse. And finally, it's painfully evident from the performance of various governments across the world that we really need competent people coordinating the emergency in the event of a novel pandemic. And that suggests that we really need politically independent agencies focused on pandemics with authority to act in every nation where we can arrange for that to happen. And ideally, these should have a mandate to coordinate with one another to extinguish nascent pandemics anywhere they might flare up in the world. Because once they're very common, it's exceptionally difficult to defend borders, even against an accident. What else can we do? Well, we can look at this equation for misuse in particular, because those other defenses would apply to both. But if we're particularly frightened of misuse, when again, it may or may not be possible, then we need to tackle this equation. We probably can't do anything about the number of people with skill in biotech. That number is going to continually rise. And it should, because there's a great deal of good that can be done with biotech. But the individual odds of misuse, well, that might be tractable if we focused on cultural change. Graduate school is famously a miserable experience, particularly in fourth year when just about everyone sinks into depression. We could focus on offering mental health support, more ethics training, and generally cautious awareness raising among the scientific community on these issues. Access also appears to be particularly tractable. If we're worried about viruses, well, in order to misuse them, you need to have one in the first place. So one way to do that, of course, is to get one from a virology lab. And virology labs tend to freely share them with one another. Instead, we could build one or more supply centers that specialize in distributing agents for legitimate research, with appropriate credentials, of course. They could also supply custom viruses made using DNA synthesis and assembly, and restrict knowledge of advances in assembly and editing of viruses to people who work at these centers, as opposed to publishing those methods and making it easier for just anyone to build and edit viruses. That leads to the elephant in the room, which is DNA synthesis and assembly technologies. Right now, we don't effectively screen all of the DNA synthesis in the world. And since it's known which companies do screen and which don't, it's too easy to actually get DNA of your choice, even if you don't have permission to access it. So we really need to improve that. It would be much better if we screened all DNA synthesis everywhere in the world. But ideally, we want to do that in a way that avoids disclosing which sequences are considered hazardous. Obviously, we should include decoys in the event that we do screen for anything comprehensively. But we really don't want to have to disclose what it is that we think is becoming hazardous, because we assume, remember, it's not possible now, we don't think. And only future advances will tell us what looks to be becoming possible. And we want to forestall the ability to experiment in those areas and discourage people from researching in those areas without disclosing that we're concerned. We might also be able to use such a method to screen DNA sequencing services. And we have launched an effort with a number of different colleagues called Secure DNA that is one attempt to solve this problem by developing a new approach to DNA synthesis screening. Now, I hope there will be many other technical attempts to do this, because we shouldn't rely on only one approach, but this is the way we're going about it. And it's pretty telling that first, we're international. We include folks from China, the US, Europe, Israel, And that's in part because that's where most DNA synthesis is done. But it's also where we have a lot of folks who are skilled at cryptography. We have several Turing laureates on our team. 2 of the 3 inventors of RSA encryption are on the team. In fact, most people on the team are cryptographers because we're interested again in building a system that can screen effectively and efficiently, but without disclosing what it is that we're screening for. The way it works is rather than searching for sequence similarity, we instead fragment the pieces of the thing that we might be concerned with. And it's designed so that one person could potentially add it to the database if they come across a hazard. But in principle, we could expand, but technically it should be just one person. If we then choose fragments from the agent of concern at random, then we can compute all functional equivalents of that. That is, we calculate which substitutions are probably still functional, generate this list, remove any that would raise false alarms and create false positives, which is the problem with the current system. That gives us a list of sequences that are important for the function of that given hazard. We then hash this system, encrypt it using a one-way mapping using a distributed oblivious function. So all the servers, say 1 in every great power, are required to do this. And you would need to subvert at least a majority of them in order to determine what is in the database. And that then gives you this database. Synthesis orders just get run through the exact same process to generate these hashed order fragments that can then just be directly compared to see if they match. And of course, anyone doing legitimate research, say a virology lab, would already have approval from their institutional biosafety committee or equivalent that they're allowed to work with an agent. And so their customer ID would simply not flag anything that they already have approval for. In other words, the system is designed to be seamless from the perspective of scientists, offering no delays whatsoever to legitimate research. In fact, we don't want people to know in the event that the thing that they're working on is now considered hazardous. So that is also by design. This may not be the way to go. I hope we come up with something even better, but this is one taste of the way that we might want to go about approaching this problem of forestalling the development of weapons that we cannot defend against until we have a chance to improve our defenses. Thanks so much to the organizers for putting this together and to the many members of my team, our funders, and really everyone who makes our work possible, especially our collaborators on Secure DNA. And thank you for your attention. Happy to take questions.
Great, thank you for that talk. So we've had a question come in. Given how difficult, expensive, and time-consuming it is to develop vaccines or drugs that perform specific desired biological functions, why should we think it will be feasible to develop artificial pathogens with desired characteristics?
Interesting question. So vaccines are indeed prevention, but you need to remember that the vaccine needs to be able to teach everyone's immune system to recognize a given pathogen. Right now, we don't know whether, say, I'm going to give one example that's very obvious to avoid info hazard. We don't actually know for certain whether improving the affinity of the receptor binding domain of a given virus for its receptor target improves the fitness of the virus. We also don't know which aspects of, I'm just going to leave it there. To the extent that we find that out, or anything else mechanistically relevant about the virus, then we could use our superior ability to design molecular interactions, think Rosetta and so forth from David Baker's lab, to build a better version. And if we did that for many different components of the virus, then we could actually privilege design over evolution. And we could do so in a way where our design attempts to build things that would be more hazardous for us than evolution is going to create. Because again, something that kills the patient is not going to be passed on very effectively. Great.
So another question, this I think referring to some of the social or cultural change things that you mentioned. So what kind of interventions, like social interventions, would be needed alongside the technical interventions? Do you have any specific thoughts on interventions like that?
So socially, much of the problem is that folks who are technically inclined tend to assume that all knowledge is worth having, which is of course trivially disproven in a thought experiment, but still that tends to be the baseline assumption. I got into this because I want to understand how everything works. That's just a baseline drive that many of us share. And we don't tend to think about the counterexamples in which knowledge is actually hazardous for us. So insofar as we can somehow persuade more scientists that this is of concern, then we're going to have fewer people who are likely to be going out there and deliberately acquiring the knowledge that they think is important for defense while disregarding the downstream risks. And again, this is a numbers game, right? The more people we can persuade, the fewer people doing risky research, just like it's a numbers game in terms of whether or not this is actually a threat. I mean, given the costs of SARS-CoV-2 and the fact that historical pandemics were worse, even if you throw aside the possibility that we could engineer something to be more destructive, if there's a 1% chance that tens of thousands of people could build a new COVID-19, we should be working to reduce that risk.
Great. And do you have any, I'm curious if there's any specific things which you've seen be successful at, like, educating scientists or convincing them that, like, certain, on being more aware of biorisks, and like how to, then maybe like, or has there not been a lot of work in this space so far?
There hasn't been a ton of work in this space. To some extent, it's generational. That is, younger scientists tend to be more amenable. I don't know if that's also why there tend to be more youthful EAs and why there aren't so many EAs who are older. It might be the same phenomenon culturally. It's a little bit hard to say. But overall, we just need more people who are willing to recognize that a 1% risk of catastrophe is too high. And even if your uncertainty is encompasses 0, then we should still work to reduce that risk. Because when the magnitude is high enough, we can't afford any positive risk in that area. The more people like that who are in the sciences to speak up and move the Overton window in the correct direction, then the better off we'll be. You don't have to go into the sciences and work on biorisk. You don't even have to be in the life sciences. You just need to speak up and say, you know what, sometimes we need to think about the consequences before we develop increasingly powerful technologies. In physics, there's a sense that we sinned, that we broke seals that should not have been broken and opened doors that should never have been opened. And that's just not true in the life sciences, in part because of the history of Asilomar and others made us think that we could handle it in advance. And hopefully we will be able to handle it in advance. That's something we can draw on, is invoke Asilomar and say, you know what did they kick down the road in Asilomar? One of the two things was the possibility that we could engineer things that would spread on their own, trivially. They said, we don't think we can do it back then. And so they said, okay, we're not going to deal with it. We couldn't agree, so they kicked it down the road. Well, now we're here. CRISPR-based gene drive means we believe that we can do it, at least for some classes of constructs. Those are defense biased, but we can always point to that. And at least for me, maybe they're just humoring me because of my role in that. But most people say, okay, yeah, it looks like it is possible and no one saw that coming. So maybe it's possible in this other space and we should be cautious.
Yeah. And on a related note, someone was asking how researchers might, what incentives researchers might have to, like, I think what this translates, like, gain access or knowledge to certain dangerous things. So like knowledge that they could use sort of to do harm. And also, like, what would be like a strong reason for people to stop them from doing that sort of work, or maybe finding that sort of, finding that sort of information out, if there is one.
So the two big incentives for science are really, it's really down to one, which is money, not for our pockets, but to be able to continue our research. And in order to win grants and funding to support our research, we need to have a reputation. Reputation comes from publications, which means that funders and journals have tremendous incentive power, to the extent that journals will, for example, decline to publish papers that say, don't show that they source their DNA from one of the IGSC companies that screen for hazards, that incentivizes everyone to only buy from IGSC companies, which then strengthens the market share of IGSC companies and improves the likelihood that we're going to have everyone screen. Similarly, if anything we can do to encourage more people to take a look at nascent projects early on, the greater the likelihood that someone will spot something that might be hazardous and say something. Because after all, most scientists don't think about this. And we're not even certain that we want that many scientists to think about this carefully. After all, if you have a lot of people whose fundamental virtue is curiosity, you don't necessarily want to direct their attention to this general area, or at least we're not sure. So there's this fine line between awareness raising and increasing curiosity in this space. I don't want to imply that we should just go out and tell everyone, oh, the sky is falling. Well, no, we don't know if the sky is falling. It's just, we believe there is a non-trivial risk that this will happen, probably within the next 2 decades. And I'm not certain that's enough time for us to develop effective defenses. And keep in mind that, again, unless we solve the cold chain problem and the distribution problem, whatever we do in terms of defenses after the thing is unleashed, even if they're effective, they're going to be delayed. They're going to be substantially delayed, especially when it comes to logistics and distribution. And as such, it's the bottom 3 billion that are going to get hit. We basically cannot defend them at all today, at all. And I'm frankly a little bit skeptical that that's going to change that much in 10 years, which means even if your program is based on identifying threats and developing vaccine-based defenses fast enough to save the rich world, we're still hanging everybody else out to dry, or at least heaping all of the risk of misuse on them while taking the fruits to protect us, which doesn't seem like the most ethical thing and certainly seems to contravene many of the most fundamental principles of EAs, at least.
Great. Well, thank you for that. Unfortunately, we are at time. There is a biorisk icebreaker right after this talk, if anyone watching would like to continue the conversation. Yeah, thank you everyone for watching, and thank you, Kevin, for this talk.
Thank you.